In this video, I'm going to talk about electric field at a point close to an infinitely large conducting and non-conducting plate. Let's consider a non-conducting plate, an infinitely large charged non-conducting plate. This is my plate with a lot of positive charges on it. I'm going to consider an imaginary cylinder. It's oriented perpendicular to the plate. This is my Gaussian surface. Yeah, that looks good. So that's an imaginary surface. It can be used to solve the problems using Gauss's law. Call it Gaussian surface. Gaussian surface. In this problem, Gaussian surface is a cylinder with this area A. Area of this face, let's call it A. This face has the same area A. And our non-conducting plate has a surface charge density. It's a two-dimensional object. It has surface charge density sigma. We don't know how many charges are there in total, but we know they are uniformly distributed and the surface charge density is sigma. This is equation for sigma. Sigma equals Q over A. I'm going to use Gauss's law to solve this problem. Closed integral E dot dA equals Q over epsilon 0. I'm going to consider left hand side. Closed integral E dot dA. This is actually the electric flux. Electric flux is EA cos theta. This is the same equation except we have a small area element dA here. It's the same thing. Okay. So we are going to consider this Gaussian cylinder and we are going to find the electric flux through all the three phases. Let's call this phase phase 1, this phase phase 2, and this phase phase 3. How do we draw the direction of the field lines? These are positive charges. Our plate is positively charged. So the direction of electric field lines are upwards, going away from this plate, just like that. But we are interested in the electric field lines through the Gaussian surface, through the cylinder. So the direction of electric field lines would be just like that. Yeah. There are a lot of them. I'm just drawing 3. Okay. What about the bottom face of the same plate? The electric field lines again will be going away from the sheet, so it's downwards. Again, we are interested in the electric field lines through our Gaussian surface, so that's the direction of electric field lines. Let's call this electric field E. Electric field. I'm going to find the electric flux through phase 1. Phi through phase 1. Phi equals EA cos theta. So consider this phase, phase number 1. I'll draw it separately. So this is our phase 1. Area vector is always perpendicular to the surface. So area vector should be upwards for phase 1. This is phase 1. This top phase. Okay, area vector is always perpendicular to the surface. So that's the direction of the area vector for this phase. What about electric field vector? Same directions, going up. Electric field vector is again upwards. That's the direction of electric field vector. So what is the angle between them? There is no angle. They are in the same direction. So theta equals 0 degrees. So phi equals EA cos 0. Let's call this phi 1. Phi 1 cos 0, which is equal to EA. So the electric flux through phase number 1 is EA. Now let's find the electric flux through phase 2. The equation is again phi 2 equals EA cos theta. This is phase 2. Area of that phase is A. Electric field is E. EA cos theta. I'm going to draw that phase. It's a bottom phase, right? So this is that phase, and it's a bottom phase, so area vector should be perpendicular to the surface. This is the direction of area vector, and the electric field lines are in the same direction. Let's draw this here. This is the direction of area vector, and electric field vector is in the same direction, downwards. The angle between them is 0 because they are in the same direction. Theta equals 0. Substitute here. Phi 2 equals EA cos 0, that is EA. So we got the same electric flux for phi 1 and phi 2. Now let's find the electric flux through phase 3. Phi electric flux through phase 3. This is our phase. We are talking about this phase, phase 3. I'll draw it here. We are talking about this shaded phase. Let's say this is the plate. Electric field lines are going up. That's the direction of electric field. This is the direction of electric field for the bottom phase. It's pointing down. So choose any point on this phase. Let's say this point. Okay. For this point, area vector should be perpendicular to the surface. So area vector should be in this direction. Area vector is always perpendicular to a surface. For this point, the area vector is towards right. You can choose any other point. Let's say this point. Area vector is in this direction. It's quite difficult to draw on a two-dimensional screen, but I think you got the idea. Yeah. So that's the direction of area vector. So you can choose any point. Always the angle between electric field vector, this is the electric field vector, this is the electric field vector, and the area vector is always 90 degrees. So the equation for phi, or phi through phase 3, is phi 3 equals EA cos theta. Let's call the area of this phase, I don't know, A3. It's different from these areas, right? So EA3, electric field is the same. EA3 cos, the angle between area vector and electric field vector is 90. Cos 90 is 0, so flux is 0. There is no electric flux for this phase. Okay, let's go back to our left hand side of Gauss's law. This is total electric flux. So closed integral E dot dA equals, we have three phases, so three electric flux values, phi 1 plus phi 2 plus phi 3. That's the total electric flux. What is phi 1? EA. Electric flux through phase 1 is EA, phase 2 is the same EA, and phase 3 is 0. So EA plus 0, 2EA. Left hand side of our Gauss's law, I'm going to call this equation number 2. This is equation number 1. Gauss's law is equation number 1. Now let's consider the right hand side of Gauss's law, Q over epsilon 0. Right hand side, Q over epsilon 0. To find Q, we have this equation for surface charge density, sigma equals Q by A. Surface charge density of this plate is sigma. Sigma equals Q over A. So Q equals sigma A. I'm going to substitute sigma A in place of Q. The equation will be sigma A over epsilon 0. Let's call this equation number 3. So we have left hand side of Gauss's law 2EA and right hand side of Gauss's law sigma A by epsilon 0. I'm going to substitute equation number 2 and 3 back in the Gauss's law, back in equation number 1. So E dot dA is 2EA. Closed integral E dot dA is 2EA. Substituting equation number 2 and equation number 3 in equation number 1. 2EA equals, right hand side is Q by epsilon 0. We can replace Q by epsilon 0 with sigma A by epsilon 0. Divide with A. Cancel out A. The equation will be 2E equals sigma by epsilon 0. We need to find the electric field, so divide with 2. E equals sigma by 2 epsilon 0. That's the electric field at a point very close to a non-conducting sheet. How do you find the electric field for a conducting sheet? The equation is very similar. E equals sigma by epsilon 0. If you draw the picture for a conducting sheet, this is my conducting sheet with a lot of charges. It's an infinitely large conducting sheet, right? That's the direction of electric field lines. But there are no electric field lines downwards because it's a conducting sheet, so it should act like a shield. It's an infinitely large conducting sheet, so big, so it would shield the bottom part. So there are no electric field lines pointing downwards. So our Gaussian surface will be a cylinder with only top part, only this top part. We have only two faces. This is face number 1. This is phase number 2. Same idea for phase number 1. Electric flux is EA cos 0 because electric field lines are upwards, area vector is upwards. So phi equals phi 1 equals EA. And for the second phase, the angle between area vector and the electric field vector is 90 degrees. So for phase number 2, theta is 90, so cos 90 is 0, so phi 2 is 0. If you add phi 1 and phi 2, you will get closed integral E dot dA as phi 1 plus phi 2. So closed integral E dot dA equals EA. Now the right hand side is, this is the left hand side. The right hand side is Q by epsilon 0. Q is sigma A over epsilon 0. So substitute it back to the Gauss's law. EA equals sigma A by epsilon 0. Cancel out A and A. We'll get the equation for electric field. E equals sigma by epsilon 0.